Now we'll make use of the derived types we described at the end of the last video to solve the heat conduction problem we specified at the beginning of that video. Many of the terms used in this video are defined in earlier videos in this JOLT. We're going to adopt a test-driven development approach, which grew out of the Agile development movement. With test-driven development, we write tests for our program before writing the program. Initially, of course, the tests fail because we haven't yet written the program to satisfy the test. Once the tests pass, the program is considered complete. In this sense, the test is a specification for the program. We're going to write an integration test, which is a test that pulls together the entire package into a complete application defined in a main program. So we'll first open and close the main program scope. Next, we'll import the global field type into the main program. The only clause here serves to restrict the import to the type and the type's public type-bound procedures. It also serves as documentation telling the reader the source module for the type. Next, we ensure that all variables must have a declared type. And now we define 3 variables of the global field type for use in time advancement and testing. Now we'll define several constants: the thermal diffusivity, the time step, the final time value, and a tolerance for the test. Then we define and initialize the time variable. Now we'll invoke the type-bound generic name global field underscore on the temperature object T to initialize the data inside T with the given internal and boundary values, the problem domain, and the number of points to be used across the domain globally. We'll leave the distribution of those points across the images to the global field type implementation. Now we use the same generic name to invoke a procedure that merely allocates memory for the object T half without initializing any data inside the object. Now we'll open and close the main time stepping loop. Inside the loop, we write expressions that implement the time advancement scheme described in the previous video. Before moving to the next loop iteration, we update the time value. After we finish stepping through time, we're going to allocate space for an object that will hold the Laplacian of the final temperature object. And finally, we'll invoke a procedure that returns the state variables inside the Laplacian, and we'll check whether any of those values exceeds the tolerance. We know from the problem statement in the previous video that the Laplacian should vanish at steady state. If the test fails, we halt all images and signal the test failure. If the test passes, then we'll have image 1 signal success. The procedure calls in this test will drive our implementation of the global field and local field types. The differing arguments for the 2 calls to the generic name global underscore field underscore suggest that we'll write 2 procedures to construct global fields, one that requires arguments and one that doesn't. The assignments to T half and T suggest that we need to bind a Laplacian operator to the global field type. The Laplacian's result will be a local field, as mentioned in the previous video. That result becomes the left-hand side argument to a multiplication operator that will bind to the local field type. The result of that multiplication operator will be a local field that becomes the right-hand side to a global field addition operator, which takes the left-hand side global field T and produces a local field result. That result of the addition becomes the right-hand side to a user-defined global field assignment to T half in one line and T in the subsequent line.